Good morning. I'm Laura Rustioni, and I will speak about reflectance spectroscopy. Of course, the results that I will show you were not obtained only by me, but by a team of peoples, and you will see all the peoples involved in the future slides. So this is the instrument that I used the most for the experiments that I'm going to show you. It is rapid and low cost. It is a spectrophotometer made by different components, so we can adapt it. However, I think it's important to highlight that the technique, the reflectance spectroscopy, could be adapted to different devices and equipments. So this is not a limit. The principle is, it looks difficult, but it is really simple, is based on the fact that pigments are able to absorb the visible radiation at specific wavelengths due to the excitation of the electrons. And this ability is really specific, so pigments absorb only some wavelengths, and so the optical properties such as reflectance of a surface is related to the chemical composition. So now I will show you some experiments that we did, but I think it's better to do not enter in details concerning the methods. I will try to show you mainly the results and the possible future applications. So first of all, we studied anthocyanins. And we did a method for the phenotypization of the color of berries, and also an index to estimate the color or the content of anthocyanins. For example, now we are still working with this approach by coupling it to other approaches, genetical and other chemical analysis to study the pink color of grapes, because there are beautiful pink colors in some grapes, some salmon pink and light purple, and we are trying to describe in detail how this color, why some berries have this color, to support the selection of table grapes, because the appearance in table grapes is really important, and we think that pink colors are really interesting. And here is missing Gabriella De Laurentiis, is also working on this subject in the genetical point of view. She studied the genetical part. Another pigment that we can easily detect in the berry, especially in white grapes, is chlorophyll. So you see two bands. This one, the main band, is chlorophyll A, and the shoulder is chlorophyll B. So we can quantify the chlorophyll content in the berry. And by comparing sun-exposed berries and shaded berries, we were able to see a modification in the spectra in this region. And by the difference between the two spectra, we can highlight the band related to the brown pigments, which are considered oxidized phenolics. And I think everybody knows that oxidized phenolics are obtained by free radical polymerization, so they are really hard to study because they are really, in one side, difficult to be extracted, and in the other side, difficult to be characterized, because this kind of polymerization is chaotic. So we have different kind of products, and we are able to detect, however, they have this common characteristic, which is the brown color. So we are able to quantify how much the sunburn damage appears in the berry by an objective method. So we developed this Browning intensity index, and for example, we studied the effect of temperature and light in artificial conditions, and we saw that these symptoms is mainly due to the overexcitation of the chlorophyll. So it is the photosystems of overexcitation which produce reactive oxygen species, and those are destroyed by the phenolic compounds in their polymerization. And the temperature did not have an important effect, so the main reason of the sunburn should be considered the light, the visible light. And we also saw that by studying different cultivars that we can group the cultivars in two types. And we imagine that this is due to the double possible role of reactive oxygen species, because they can act as oxidant and produce a lot of brown pigments, or they can also act as a signaling, and the berry can adapt to the stressful conditions. And so we can also phenotype the cultivars to select more resistant varieties. For example, for table grapes, it could be important to do not have symptoms of sunburn. Another thing that we saw is that during ripening, if we do not have anthocyanins, so still in white berries, during ripening we do not have the accumulation of specific colored compounds, but the yellowish color that we obtain should be considered as a consequence of catabolic processes, such as the different degradation of chlorophyll and carotenoids, which have a different ratio, and the accumulation of oxidized phenolic compounds. And now we are studying on the comparison between ripening, because we know that the ripening process is characterized by oxidation. At the horizon, reactive oxygen species are produced as a stimulus for the ripening. So we are comparing ripening and sunburn to see what happened similar and different. And in the future, we would like to work on artificial ripening for phenolics to try to find some artificial way to improve the ripening of those compounds. So let's move to woody tissues. So another subject that we studied by reflectance spectroscopy is the characteristic of the stems of the woody tissue, especially to find drought resistance, drought tolerant varieties, or however to study the vine answer to drought conditions. And what we saw first in the first preliminary experiment is that drought modify the tissue, the woody tissue, by changing its reflectance spectra. So there are chemical modification into the stems, but we did not know exactly what changed. So we were working with unidentified compounds. So a limit of this technique is that is able to detect only pigmented compounds. If a molecule is not colored, we cannot detect it by this approach. However, it is we have a lot of historical knowledge made by microscopy, which concerning stainings, which can color specific class of compounds or specific compounds. So the idea was to produce on-solid reactions and to quantify the compounds by a fast approach. One of those analyses require a couple of seconds, and the coloration maybe can require, the two that I will show you require 3 or 5 minutes, and you can manage many samples in the same time, so it's really much faster than microscopy analysis. And what we did, for example, is to study the hydrophobicity of the woody tissues by a reaction with Sudan 4, which is a dye, it's a red dye, which interact by hydrophobic interactions with hydrophobic compounds. So as much as hydrophobic compounds I have in my tissue, as much red color is retained in the tissue. And we did this reaction. We tested 10 different vitis species, so very different plants. And we saw that the hydrophobicity of the stem was strongly correlated to the expected drought tolerance of the different species. And we think that this approach, as it is fast and low cost, could be a good support for new rootstock selection. Another index that we just finished to develop, it is submitted, the paper is not published yet, is related to the starch quantification, because the starch is really important as a stock, as a reserve for in the woody tissue, and it is important both for the drought tolerance and the frost tolerance. And we made a reaction with iodine, and we found this is, the light gray is the spectra of the tissue before the coloration. The dark gray is after coloration. This is the difference, and it is the spectra due to the reaction. And for the moment, we just looked the total starch content, but probably we will be able also to discriminate between amylose and amylopectins, because the shoulders are due mainly to one or the other of those compounds. And and we think that, for example, this could be an interesting technique to support nurseries to test, to check the quality of the cuttings and to produce high quality plants. And so now the next step was to test those on solid reaction approach for the drought response of the plant. This work is mainly done with Paolo Civilotti and Jose Carlos Herrera. And those are the really preliminary results, and we are still elaborating the data. However, we think as we saw that the drought condition produce significant modification in the stems. And so, of course, it is important to remind that stems are the reserve organs of the plants. So they manage the use of the water during the vegetative period. So we think it's important also to take them into consideration, because often the leaves are the main part of the plant detected. However, also stems play an important role. So the next step, we are already preparing the experiment, but I do not have results for the moment, is to move to leaves. And we will study mineral deficiencies. So we are preparing the experiment to check different mineral deficiencies, and we think if we will be able to produce indexes, maybe they could support the fertilizing management or precision viticulture in the next future. But this work will be done with Daniele Grossi, and let's hope to have good results. And I thanks all of you for the attention and all the people who participated to those works.